All right, so let's solve this computer's problem that we already developed, its LP model. Okay, and when we say let's solve it, we're going to solve it graphically. And what do we mean by solve it? That means find the solution. What's the solution? Means that find the value of x1 and the value of x2 that would maximize my profit. Okay, this is what we mean by solution. Because we have only two decision variables, so we are looking into two axes, right? X1 and X2. So you can give the horizontal for X1 and vertical for X2 or vice versa. It's up to you, okay? But you have to be, of course, consistent. So what to do next? We're going here to use our constraints in order to minimize our search area. You see here, our search area is the whole space. Remember, we talked about the feasible solution space, and it's only the constraint that is going to reduce this search area for us. All right, so I'm going to use the non-negativity constraints first because they really reduce our search space significantly. While without these, I can look here, I can look here, I can look here, or I can look there, right? But with the non-negativity constraints, I will get rid of all these, right? Because they are not feasible. Why? Because look at this, for x2 greater or equal than 0, it's only the upper part. Okay, it's only these that are feasible for me. And for x1 greater or equal than 0, it's only the right-hand side that is feasible. Now you can see that it's only this quadrant, okay? It's only this quadrant that has an overlapping between these two constraints. And that's what makes now only this quadrant to be the feasible for me. Before I proceed, I just need to take out these because they may distract you later on. The one on the other side, I can leave them, okay, because I don't need them anymore. So here we go. You see, we call that blue area the feasible solution space defined by the non-negativity constraints. You see how two constraints have really shrunk my search area by 75%, which is great. Next, I'm going to use my next constraint. So I'm going to use the assembly constraint. The constraint says 4x1 plus 10x2 less or equal than 100. How can I plot a less or equal or an inequality? We know how to plot an equality, right? Because it would be a straight line. And this will be almost the same. So I'm going to replace this greater or equal with the equal. And when I plot the line, this will be the border between two areas. And I'm going to search which area represent the less or equal. Okay, so here we go. I'll start by plotting the line representing 4x1 plus 10x2 equal to 100. How to do that? You set x1 equals 0, you find x2, you set x2 equals 0, you find x1, or you find any 2 points and then you join them. All right, and here we go. This is our line. And now what we need to do, okay, this I'm giving it the name also. We need to find the feasible space. So which means that which side of this line represent my or meet my requirement. Is it here or it's there? Now some of you may say that isn't it obvious that less or equal is certainly this part, which is the part lower than the line. You're right here, but it's not always as clear as here, right? So what I strongly advise you to do instead to test it. How to test it? We take any point where I know that it is located in which side. I know that point 5, 5, which means x1 is 5 and x2 is 5, okay, is below the line. And I'm going to test this one in my inequality. So I will replace x1 with 5, so 4 times 5, 20, plus 10 times 5, that's 50, plus 20, that's 70. It is less than 100, which means, yes, the area under the line, which is now the red area, this is my new feasible solution space. But this is not yet done, right? I need to finish or I need to finalize my feasible solution space by using all the constraints. Okay, so this is where we ended in the previous steps, and this red area is now sorry, is the feasible solution space. That is the result of the non-negativity constraint and the assembly constraint. So let's use one more. We have the inspection constraint. I'm going to go quickly here because these are exactly the same steps. So I'm going to plot the line to x1 plus x2 equal to 22, and I'm going to test it for the inequality, which part represent the less or equal. So I'm going to pick also another point where I know where it is, on which side of the line. So also 5, 5, I'll plug it, 2 times 5, 10 plus 5, that's 17, which is less or equal than 22. So now what I can find is that this area, all that area, meets the inequality. However, because I need the solution to be meeting all the constraints, I can see that out of this hashed area, it's only this part that is that has an overlapping with the red area. Okay, so this part, yes, it is feasible for this green, for the inspection constraint, but it's not feasible for the other one, for the assembly constraint. So I will take it out. This will be out. Okay, and I will be left with only this part. Okay, the green part. This will be our new feasible solution space. Okay, so this is a much cleaner illustration for you. We ended up with the green polygon here, and we call that the feasible solution space that is defined so far by the non-negativity constraint, by the assembly time constraint, and by the inspection time constraint. And we are left with only one more constraint, which is the storage space constraint. So let's do it. All right, so let's add the last constraint that we have to see how much we can still reduce that feasible solution space. Okay, so we have this storage constraint. Again, we'll do exactly the same steps as we were doing before. This is our line, and we need to test for the inequality. And here we go. And also here, it's exactly the same concept. The whole thing here, all that area, satisfy this new constraint. However, you can see that part of this area is not overlapping with the green area. So you can see that the green area will be reduced. Will be taking out this because it does not meet the new constraint. And also this part, it meets the new constraint, but does not meet the old ones. So they will be also out. All right. So we will end up with only the yellow part. Okay, this will be our final feasible solution space because that's it. We have exhausted all our constraints. Okay, so again, this is a much cleaner illustration for our final feasible solution space. Here we go. This is a final feasible solution space because we don't have any more constraint to add. It meets all the requirements. A quick note here before we start the next step to find the solution. It's very important for you to understand what do we mean by feasible solution space. That means any point here. Look, for example, if I take this one, any point has an x1. Sorry about this. It has an x1 here, and it has an x2. And this combination of x1 and x2, they meet all the requirements. You can be sure about that. So, and remember that this solution space also, or part of the feasible solution space, is the border itself. So if I take a point here on the line, yes, it's also feasible. So it has also another x1, another x2, and when you plug all these x1 and x2 in the constraint, you will see that they respect the inequality. All right, so next we're going to solve it, find the optimal solution, right? Because these are feasible solutions, not necessarily optimal, or in fact, they're certainly not optimal. We want to find the optimal one.